role of correspondences in the constructions of set theoretical solutions to the n-simplex equations. So that would be the plan of my talk. Yeah, okay, I will be maybe I'll do it a full screen. So that will be the talk, plan of my talk. So is the second slide visible? Sometimes it is not, you cannot see when I change slides on the full screen mode. So do you see the slide outline? Okay, great. So that would be the plan of my talk. So in the first part, I will say a few general things about n-simplex equations. However, the main focus will be on methods for construction of 3 and 4 simplex solutions to the 3 and 4 simplex equations. So the second part of my talk, in the second part of my talk, I will explain what are tetrahedron maps and what's their relation to matrix defactorization problems. And I will show you a new approach for constructing such maps, which is joint work with Sergei Gonin. And in the last part of my talk, I will show you a method for constructing 4 simplex maps as non-trivial extensions of tetrahedron, Zamolodchikov tetrahedron maps. So what are n-simplex equations? N-simplex equations are just higher-dimensional generalizations of the famous Yang Baxter equation, and they appear in many diverse branches of physics and mathematics, pure and applied. However, this is an integrable system stock, so the basic interest to us is that they are strictly related to continuous and discrete integrable systems. So in what follows, I just wrote down the 3 most famous members of this family of simplex maps. So the 2 simplex equation is the famous Yang Baxter equation. The 3 simplex equation, which is known as Zamolodchikov tetrahedron equation, and the 4 simplex equation, which is known as the Bazhanov-Stroganov equation. And I will explain in a bit what the upper indices are, although most of you already know. So the talk is based on the study of set theoretical solutions to such equations. And the first such solutions appeared in a work of Klianin in 1989. However, formally, the study of set theoretical solutions to the n-simplex equations in the case of the Yang Baxter equation, the 2 simplex, was formally proposed by Drinfeld in 1990. So the term n-simplex map is motivated by, it was used first by Buchstaber in the study of solutions to the Yang Baxter equation in a arbitrary topological space. And then it was formally proposed by Veselov in 2003. However, the main result, which is the basic result, I think, in the theory of set theoretical solutions, which is the basic element in the construction of and classification of solutions, is the fact that the local n-1 simplex equation generates solutions to the n-simplex equation, which was a statement appeared first in 1989 in a paper of Maillet and Neyhoff. And these also are used, can be considered Lax representations. The n-1 simplex equation can be considered as a Lax representation for n-simplex maps. So Dimakis and Miller-Huijsen in 2015 wrote very precisely what these equations look like, and we will show them in a bit. So this talk, as I said, is devoted in the development of methods for constructing solutions to 3 and 4 simplex maps, which can be generalized for constructing n-simplex solutions to the n-simplex equation. So what are tetrahedral maps and how they are related to the local Yang Baxter equation? So let's start with a set, any set X capital. So any map which takes three elements of this set and gives three new elements U, V, and W, which are functions of X, Y, and Z, will be called the tetrahedral map if it satisfies the Zamolodchikov functional tetrahedral equation, which looks like that. So the upper indices denote the following. So all these functions with indices, upper indices I, J, K, act on a set of 6 elements, and the indices I, J, K may mean that these functions act on the I, J, K of this set of 6 elements exactly as the map indicates, and they act on the rest in a trivial way. So, for example, T with indices upper indices 1, 4, 5 means that this function acts on the first, the fourth, and the fifth element exactly as the map. So it changes the first, the fourth, and the fifth to functions of U, V, and W of x1, x4, and x5, and the rest remains as they are. Probably the most popular example is Kashaev's electric Naistor transformation, which looks like that. So x, y, z are transformed to these functions U, V, and W of x, y, and z. So it's a birational map, which means that it's rational, and the inverse is also rational. And here, sorry. And here I have listed some of the most important results for me that are obtained on the tetrahedral maps. Okay, there are many results, that these are probably the basic most important results. So the Sergeyev's classifications. Sergeyev presented in 97 and also together with Kashaev and Korepanov in 98 a list of maps generated by certain matrices. I'll show this list a bit later. A very important result is the relation between tetrahedron and pentagon maps, and in general N-simplex maps and N-gon maps, which is a work by Dimakis and Miller-Heusen, and has very deep geometrical meanings, etc. Moreover, the relation, so the work by Kostakis, Nisporsky, Papageorgiou, and Togas in 2019 on how you can construct, how you can derive tetrahedral maps from 3D lattice equations using symmetries and vice versa. And also this fully non-commutative examples of tetrahedral maps related to the Desargues lattices, work of Doliva and Kashaev in 2020. So how these tetrahedral maps are related to matrix factorization problems. So a tetrahedral map can be generated by a simple 2x2 matrix. So consider a matrix of this form, so a 2x2 matrix with elements functions of X. For this talk, I will stick to scalar rational functions. However, Korepanov has considered matrix matrix blocks for this. So A, B, C, D in general can be matrices, and you can refer to a work of by Korepanov. For this 2x2 matrix, one can consider the 3x3 extensions or generalizations, whatever you prefer. So how do we consider this generalization? So we introduce this notation. So L12 will be the following 3x3 generalization of the matrix L. So the indices 1 and 2 means that the elements A, B, C, D sit on the intersections of the first and the second row with the first and the second column of this 3x3 matrix. 1,3 means that they sit in the intersections of first and third row with the first and third columns, etc. So we substitute these matrices to the following equation. The following equation is well known as the local Yang Baxter equation, but unlike the terminology that Kashaev used in one of his talks, he used to call this equation Maillet-Neyhoff equation in Korepano's form. So this is very precise, long but very precise. So if you substitute these matrices to this equation, you will obviously get a set of polynomial equations for u, v, w, z, x, y, z. So if this set of polynomial equations has a unique solution for u, v, w, you can say that a map is defined uniquely that takes x, y, z and gives you functions u, v, w of x, y, z. This map is always a tetrahedron map if this is a unique solution. However, there's no proof for this statement. You always need to check, but there's no counterexample. So I will show you later on some supplementary relations that must be satisfied in order for this map to be a tetrahedron map.
Satiris, may I ask you? You say equations are polynomial, but functions are rational. How it happens that equations polynomial when functions are rational?
Yeah, okay. You can turn them. Well, should be, yeah, you're right. Should be some a system of equations, not necessarily polynomials, that you can multiply and bring them to a polynomial form. So, well, okay, a system of equations for u and w, x, y, z. So if the system has a unique solution for u and w, it turns out that this map is a tetrahedron map.
But polynomial in A, B, C, D.
Well, in all the examples will be polynomial. Well, I have also some simple rational, yeah. But okay, let's say that polynomial in functions of x. So, and this if this is true, then equation 1, according to Dimakis and Müller-Huijsen, will be called the Lax representation for this tetrahedron map. So let me show you an example. So starting with this simple 2x2 matrix. So x is one variable, k is just a parameter. We define its 3x3 generalizations. So after substitution to the local Yang Baxter equation, we get the following system equation. So the local Yang Baxter equation is equivalent to this system of equations for u, v, and w. This system has a unique solution for u, v, and w given by this following expressions, which means that this map is a tetrahedron map, the associated map. However, as I said, there's no proof for it. You always need to check. Right, so and here I just wrote down all the classification list by Sergeyev. So I just wrote the matrix generator and the map that is generated by the local Yang Baxter equation. So that's the first matrix, that's the second case, that's the third case, fourth case, fifth case. There's also the fifth case actually gives rise to this Kashaev's electric network transformation, which I wrote a little bit earlier. There's actually one more case which I missed, which is related to the Ising model, and yeah, I should have written it down. So that's Sergey's list of maps. And how however, there's a more general approach for constructing such maps, again by the local Yang Baxter equation. and I will demonstrate it now. So in Sergeyev's list, there are only consider maps that uniquely satisfy the local Yang Baxter equation. However, if X is a set, we will demonstrate that correspondences between X cubed and X cubed give rise to new tetrahedral maps that do not belong to this list. And this can actually lead to much wider classification results if our task is to classify the actual solutions to the local Yang Baxter equation, the generators of tetrahedral maps. So the task is to classify these generators of tetrahedral maps. So okay, let us demonstrate this by this very simple example. So we get this simple diagonal matrix with elements X and 1 over X, and consider this 3 by 3 generalizations exactly in the way we showed earlier. So these elements sit on the intersections of the first and the second line with the first and the second column. This is L1. So that's how we define this 3 by 3 generalizations or extensions for everyone. We substitute them to the local Yang Baxter equation. And in this case, the local Yang Baxter equation is equivalent to the system of equations where we can express U and V in terms of V. So this is not a map, but it's a correspondence between the complex field except 0 cubed with itself. If we fix, so in order to define a map, we need to fix the free variable. The free variable is V. So if we fix the V to be X, we obtain this map, and this map can be checked to be a tetrahedral map. However, this correspondence does not define tetrahedral maps for any choice of V, but only for a particular. But it could be infinite, many choices. I will comment later on how to find how one can find these particular choices. So I wanted to show you a list of maps. All of them are appear in our paper with Sergey Gonin. You can find on our archive. So the list of 4 maps are generated. All of them are generated by this matrix, and for several different choices of the free variable. So for various choices, you obtain these 4 maps. So you can say that this map has this lax representation. And all of them share this functional independent invariance. And also, you can get a second list of maps together with invariants, all of them generated by this matrix. So that has the same matrix, but the elements are placed on the anti-diagonal. Again, you get a correspondence, you get a free variable, and for a particular choice of this variable, you obtain these maps. And these maps, I repeat, they don't belong to any of the known classification lists. However, all these maps in the previous propositions are linearizable, and they were studied by Hietarinta, but we present their lax representation. So we construct them by the local Yang Baxter equation, and how they are linearizable. So if you change, for instance, here in the first map, if you change X to E to the power X, Z to the E to the power Z, and Y to the E to the power Y, and also this U, this is a function of U, to the E to the power U. here x times z will be in new variables will be x plus z, and this will be y minus x. So all these maps do appear in the work of Hietarinta, but you can how you can construct non-linearizable maps. You need to change your set. So we started with a set to be the complex field. Now we change X, we consider X to be a non-commutative group. So we start with this matrix, substitute to this local Yang Baxter equation. Again, we obtain some correspondence. The correspondence has a free variable. For particular choice, we manage to quantize some of the maps. So these two maps are tetrahedron maps on non-commutative with non-commutative variables on non-commutative groups. They have this lax representation, and also if you take the second matrix that I showed earlier with elements on the anti-diagonal, you get these two maps on non-commutative groups again. These are non-linearizable, so they don't. You cannot linearize them to obtain Hietarinta's maps. And also I wanted to show you some examples. So okay, there are many examples on division rings, but that's one of the examples. So let R calligraphic be a division ring, and Z over be its center. So we consider this matrix. So this matrix is not arbitrarily chosen. So it's from an older work with Sasha Mikhailov and Pavlos Xentidis on classifications two by two Darboux matrices for NLS type equations. So this is one of these matrices by change of variables. So we consider these elements to belong to be ring elements, except of the parameter H that belongs to the center. And we consider the 3 by 3 generalization of this matrix in the way we explained before, and substitute them to the local Yang Baxter equation. Again, this local Yang Baxter equation is equivalent to this following correspondence. So here you have U1 is your free parameter. So the question arises as to whether for particular choices of U1 you can get maps, tetrahedron maps. It turns out for the choice, if we fix U1 to be Y1, then it's like if we obtain this map, you can prove that this is a parametric tetrahedron map. You see it has parameters N, B, and C, and it has the following invariants. However, we here is not fully non-commutative. We do this. I don't remember how Pavlos is calling it, and Oliva, I think it's called centralization. So you consider some of the variables to belong to the center. So it's not fully non-commutative. Here, I assume that this x variables with indices 1 belong to the center of the ring, and the rest can be fully non-commutative. So this do not commute. This x2, z2, z2 with y2 minus 1 do not commute. And then you can restrict this map to this invariant leaves on the level sets of the invariants to a fully non-commutative. And in fact, if you do so, you will restrict to a family of maps with a parametric family of maps with parameters A, B, and C. And if you choose A, B, C to be the same variable, K, then this map boils down to this to a non-commutative, fully non-commutative version of Sergeyev's map. This is one of the maps that I showed earlier in Sergeyev's list. Obviously, there's the natural question how to prove that a non-commutative map is a tetrahedron map. So, because in the commutative case, we just use Mathematica and we check it very easily. So, obviously, with straightforward substitution, but it's very difficult if you are working with non-commutative variables. There are some packages actually. There is a package that Sergey found online. I think it's called non-commutative algebra, and it works for simple maps. Well, I tried earlier today for a map in Doliva's paper, and it doesn't simplify enough to give you 0. Although by hand you can do it. You can prove it by hand using the following theorem. So the following theorem actually is a generalization of the three-factorization property that was used by Papageorgiou and Kouloukas in 2009. So that's a generalization for the case for simplex maps, and it goes as following. So it works in general for parametric maps. So you have what is a parametric tetrahedron map? So to every variable you assign a parameter. So here it should be C. It's a typo. So Z goes with C. And then you get pair of elements, U with variable S, V with parameter B, and W with parameter C. So let's say that this is this map satisfies the local Yang Baxter equation. So you substitute it here, and the equation is satisfied. Is it a tetrahedron map? How we can check? So we need to consider the 4x4 generalization of matrix L. I will show you later on in an example how you can do it. And this, if this condition here implies the trivial solution, so that t hat is equal to, so all the hats are equal to the variables without hat, then the maps you can prove that the map satisfies the parametric Zamolodchikov tetrahedron equation. I have to comment that Talalayev, Bitchkov, and Kazakov, I don't remember if there was another author. Please, Dima, correct me. So they showed some similar statement using graph theory. So how does first of all, why this statement also works for correspondences? Not only convenient to work with this condition, because you don't need to use the map at all. You just use the matrices that generates it, and I'll show you in the next example. So the next example is the non-commutative Hirota map. It appears in a work of Doliva and Kashaev, and is generated by this matrix. So X is a variable that belongs to a ring, a division ring. So we consider the 3x3 generalization of this matrix. And as usual, we substitute it to the local Yang Baxter equation. So this local Yang Baxter equation is equivalent to this system of equations. And this system has unique solution for UVW. It defines the following map, which is the non-commutative Hirota map. So how to check if this map is a tetrahedron map? You take the same matrix, L, and you consider its 4x4 generalizations. So 4x4 generalizations is that means that again the elements of this 2x2 matrix, this is the notation again, so they sit again in the intersections of the first and the second row with the first and the second column, and you get this 4x4 dimensional extension. all these matrices you substitute in the matrix refactorization problem, and the only thing you need to show is that this from this matrix refactorization problem implies that all the hats are equal to the variables without the hat. And it's very easy to do because, look, I mean, this is equivalent to this system here. And as you can see, actually, they pretty much straightforward. I mean, you get straight away, you get the S hat is equal to S, Y hat is equal to Y, R hat is equal to R. So from here, you get straight away that X hat is equal to X. And then you substitute here from here, you find the Z hat is equal to Z. So they follow pretty much immediately. And then you prove that this is a tetrahedron map. And also an important comment that so because in the previous slides I showed how you can produce, how can you derive new maps and in principle obtain new classification results if you allow the local Yang Baxter equation to if you consider also correspondences as solutions to the Yang Baxter equation. But I would always fix the parameter, and the question is, how do I choose the parameters? Well, first of all, how we usually do it, usually out of experience, we know pretty much what variables do. But if you want to do it formally, so you can use again this. So this statement says that so if this matrix factorization implies the trivial solution, then the associated map is a tetrahedron map. So if you get a correspondence, if a matrix by the local Yang Baxter gives you a correspondence instead of a map, then this matrix refactorization will not give you the trivial solution, will give you something different. And you see what choices you can make so that you get the trivial solution. So the 6 factorization problem indicates some of the choices that you may make in order to obtain a tetrahedron map. So, and okay,
yes,
we now
could you comment what kind of solution for the tetrahedron equation you obtain in this example?
Sorry, if I can comment which kind of solutions to the tetrahedron equation I obtain?
Yes. Am I right that this example produces?
No, this example gives you, this example has a unique solution. It's not a correspondence if you're talking about Hirota, non-commutative Hirota map.
Okay.
So here I didn't make any choice. But the choices are usually something here instead of R hat, you will get R plus another variable. So you will get them in pairs. So R hat plus S hat is equal to R plus S. So usually there are simple choices you can make. They are not the only ones. So this 6 factorization problem does not show you all the choices that you can make in order to obtain a tetrahedron map. However, when you get a correspondence as a solution to the local Yang Baxter equation, I consider all the solutions, all the maps all tetrahedron maps that are being defined from the correspondence. I consider them somehow equivalent. So I think that an important question is to classify the correspondences and not the solutions that they generate. Okay, so we saw how in principle we can construct tetrahedron maps, how we can construct solutions to the Bazhanov-Stroganov equation. Well, obviously, you need to make the tetrahedron equation local and then use it as a generator of solutions. So here, my focus will be to show you how you can extend non-trivially your 3 simplex maps in order to get solutions to the 4 simplex equation. So let's start with what is 4 simplex equation. Again, we'll start with a set. So a 4 simplex map is a map that takes 4 elements of this set X, capital, and gives you functions of these variables, U, V, W, R, and will be called a 4 simplex map if it satisfies the 4 simplex equation, or Bazhanov-Stroganov equation. Again, the indices here mean that indices I, J, K, first of all, these functions are defined, are acting on a set of 10 variables from the same set X capital. So the indices I, J, K, L mean that these functions act on the I, J, K element of this set of 10 elements, act as the map S, and they act on the rest trivially. So S1, 5, 6, 7 means that I will act on the 1st, 5th, 6th, and 7th of this set of 10 variables exactly as the map indicates, and on the rest trivially. So I will change X1, X5, X6, and X7. I will change them to functions U, V, W, and R of these variables, and the rest remains as they are. In principle, how you can generate this solution since via the local tetrahedron equation. So you get a 3x3 matrix where its elements belong depending on a variable x, and you consider their 6x6 extensions. Again, the notation is as usual. So one example of such map is, well, the upper index 6 means 6x6 extension. 1, 4, 5 means that the elements of this matrix, A, B, C, D, E, F, K, L, M, sit on this on the intersections of the 1st, 4th, and 5th row with the 1st, 4th, and 5th column of this 6x6 matrix. And you consider all these possible generalizations. And this is actually the local tetrahedron equation. Yeah, so this local tetrahedron equation is a generator of solutions to the 4 simplex equation. Again, we'll use this Miller-Huyssen's terminology. We will call them Lax representation. So a local tetrahedron equation will be a Lax representation for potential solutions to the 4 simplex equation. So how can we extend non-trivially solutions, tetrahedron maps to 4 simplex maps? First of all, what is a trivial extension? A trivial extension is the following. So if we have a map that takes 3 variables and gives you 3 functions, a tetrahedron map, how you can trivially extend it, so you just trivially add 1 variable here, t. And this map will be automatically a 4 simplex map, is very easy to prove in half a line. So we want, and this maps will be called non-trivial. So will be called trivial. So we want to construct extensions where here there is a function of all variables x, y, z, t, and this also u, v, w also depend on t. How you can do it? So given a map like that, there's no way that you can understand what to put here in order to obtain from this map to obtain a tetrahedron map. But what you can do instead is you can, instead of trying to extend this tetrahedron map like that with guessing, you can just extend the generator of the tetrahedron map. So what do I mean? So recall the following. So if we have a tetrahedron map that looks like that, with lax representation, the local Yang Baxter equation for some matrix 2 by 2. This is usually this is how we generate the tetrahedron maps. So how can you let us first understand how I can trivially extend this lax matrix to get the trivial extension. So I just add one here. Consider this 3 by 3 matrix. I add the unity here, substitute it back, and I will get exactly this map. It's also very easy to check, and is probably to most of you, to some of you, is obvious. So the idea is the following. So instead of this trivial unity here, to consider a new variable. Let these matrices A, B, C, and D be functions of one variable, and add one more variable, such that on the limit x2 goes to x1, we get the matrix that gives you the trivial extension. And substitute this matrix to the local tetrahedron equation, and we aim to obtain a correspondence which, for particular values of the free variables, we will be able to define for simplex maps. And as an exercise, we'll do it on Sergei's map. So let's get this first. The first example of Sergei's map. So this map, and we want to get a 4-simplex non-trivial extension. So this map here has this generator, as we saw earlier. We just generalize this generator. So we add one variable here, and this matrix of 2 variables we substituted to. We consider, obviously, was substituted to the local tetrahedron equation. But in order to do so, we first need to introduce this notation. We need to write down this 6 by 6 generalization of this matrix. So we write them down. We substitute to the local tetrahedron equation, and we see that this equation is equivalent to this correspondence. For example, if we all of it is expressed in terms of W2. W2 is our free variable. So if I choose W2 or T2 or W2 to be Y2, the above correspondence defines a 4-simplex map. These 2 4-simplex maps. You can substitute and check that these are 4-simplex maps, and they are birational also. Oh, no, actually, the first one also is birational. And this also you can do for other maps of the Sergei's classification, and you get this list of maps. You just add the extension I showed is the simplest non-trivial extension, and it gives you already gives you nice results. So but let me comment a little bit on that. So first of all, here I consider, where was that? So here I took this map that generates a 4-simplex tetrahedron map, and I consider the simplest non-trivial extension. But here I didn't allow functions A, B, C, D to be also function of x2. So you can allow them to also depend on this new variable. At the limit, they will again go to the original map. And you can get also even more interesting results. But here you need to be careful to preserve the derivative, the determinant. Sorry. And actually, if you allow them to be functions of x2 as well, you can see that you can also extend non-involutive tetrahedral maps to non-involutive, which is a quite important observation, because involutive maps have trivial dynamics, non-involutive maps have more interesting dynamics. So you don't only get an extension, but you get a non-involutive maps. And also, so the next step is obviously, I said, okay, I'm moving to conclusions now, but okay, I'll comment on that again. So the task is the following. So we know that where was it? So yeah, we know that this 3x3 matrices generate via the local tetrahedron equation. They generate 4 simplex maps, and the idea is to classify all these matrices, to classify solutions of the local tetrahedron equation. So one classification that we're doing at the moment is we replace all these elements by variables. And an important, interesting, very interesting fact is, you know, I wrote here, I was obtaining non-trivial 4 simple extensions by this matrix. So it turns out that if you replace any of these 4 zeros by a non-zero element, then the local tetrahedron has no solutions at all. So the maximum allowed, as I said that 4 simplex maps are generated by 3x3 matrices. What I didn't say is that it turns out that the maximum non-zero number of elements here is 5. So you cannot get any 3x3 matrix with 6 elements that solves the local Yang Baxter equation. Sorry, the local tetrahedron. And after some experiments, I believe that there are okay. The general task is to classify all solutions of the local N-simplex equations and not their corresponding solutions, and allow correspondences also to play their role. But when experimenting, it turns out that all the local simplex equations, local N-simplex equations, when N is an even number, and when N is a non-even number, they are different actually. So here in this tetrahedron equation is a 3 simplex. The local tetrahedron equation is the local 3 simplex equation. So 3 is an odd number, and that's why you have all these restrictions on this on the number of non-zero elements. So it would in examples it looks like the local N-simplex equations with N being odd have an even block of non-zero elements and then a trivial extension. It looks like that. I may be wrong, but so far it looks like that. I don't know. I think maybe Dima can comment on this. I think something he mentioned in the past about odd and even local and simplex equations. But let's summarize. So in this talk, we showed how we can construct 3 and 4 simplex maps using matrix refactorization problems using local 2 and 3 simplex equations. And in this way, you can construct in general N-simplex maps. We do have examples of N-simplex maps, not many, but we do have some, and also non-commutative on groups. Actually, for this map that in the non-commutative case on groups that generated by this matrix, let me show you. So Sergey managed to guess what the generalization of these maps looks in the N-simplex case. So here we have x1 1 over x, x1 over x, and in the N-simplex we'll have a matrix where on the diagonal you have x1, x2, x3, and the last element will be 1 over the product of all this x1, x2, x3, and get a very nice N-simplex maps and simplex map on groups. However, I agree with Dima's intuition. So there should be, I haven't written it here, but there should be a deeper reason why this four-simplex, this correspondences give rise to N-simplex maps, and maybe the right language to classify them is on multi-valued groups. Actually, Buchstaber came here and gave us a talk on multi-valued groups, and it probably makes sense to write to think about classifying the correspondences on multi-valued groups and not on arbitrary groups. So, okay, that's pretty much what I wanted to say. So thanks very much for listening.
Thank you very much. Very interesting talk. Are there any questions, please?
Yeah, sorry.
Go ahead, Sasha.
You talk about classification. That means you have some equivalence relation in classes.
Yeah.
Because classification is class representative in a class of equivalence.
Well, I don't have classification yet. I just.
No, you say classification so many times. What classes? What's the equivalence you mean?
Gauge equivalence permutations.
Permutation, right?
Yeah.
And second part also related. In Yang Baxter, what I bit familiar with, and integrable system, we have some kind of gauge transformation, or even very simple gauge transformation, right?
Mm-hmm.
So then it should be analog of here, of this transformation, which relate different maps, I would say. Right?
Yes, there is. Yes, of course, there is a definition about very similar to gauge. Yes, there is a definition.
So then probably matrix which with your 4 zeros can be make non-zero by just conjugation.
Look, the thing is that first of all, let me repeat that I don't have classification results, but we are working on it, and we found out, actually, my student found out that okay, maybe I can show you actually which are for simplex equation, which are the possible maps. Give me a second. I need to stop sharing and then share my screen. Yeah. Just give me 1 second. I'll find this file and I'll try to share my screen so that you can see the file. So I want to say that the answer to your question is possible. Yes, you can then retrieve all by. I'll write you the more general matrix, and all the rest follow if you take zeros. Let me try to share a screen. So I think you can see my screen now, yeah? So in the case of of the solutions to the local tetrahedron equation, these are the general maps. All the rest follow if you put 0, one of them. But I have to say, but in this classification, you don't allow relations between them. Well, you cannot make very general classification that covers everything. That's just probably not possible. So we started by that. So all these non-zero elements, okay, here it says what you are allowed to do. I think you can read Russian. So here are all the matrices that all the rest of correspondences follow are generated by these matrices. If some of them you put them equal to 0. But you don't allow any relations between them. If you allow any relations between them, actually, you can even probably retrieve all the maps in Sergei's list and on all our maps, etc., for some change of variables or limits. But that's the more general ones.
Okay, thank you. We can discuss it later.
Yeah, sure.
Can I pose a question?
Yeah, sure.
The question is about spectral parameter dependence.
So I don't see, but the voice sounds like Frank, I guess. Yeah.
Yeah, it's me. Sorry.
Yeah.
Okay.
It's
about spectral parameter dependence. Is there any spectral parameter dependence? Because I didn't.
No, there's no spectral. Actually, there's no spectral parameter, and it cannot be. It can only be for Yang Baxter maps. So after in n equals 3 and over, you just forget about spectral parameters. Is similar to what is true in integrable systems. So you have spectral parameter in 1 + 1, but in 2 + 1, the spectral parameter plays the role of the derivative with respect to the second special variable. So there's no spectral parameter, unfortunately.
Okay.
May I pose a question?
Yeah, sure.
Yeah, this is Volker speaking.
Yeah.
In some of your theorems, you have this condition that the equality of certain strings of, let's say, lax maps implies or shall imply that the parameters are equal on both sides. This condition simply equivalent to the condition that the lax equations determine uniquely a map. I think this condition first appears.
No, actually, you can. Yes, I'll comment on that. Look, the thing is, for this theorem, there is a proof. So this theorem, as it is, it works. As it is, it works only when you're right. It works only if the lax representation as a unique solution. However, if you have a correspondence, you use the trivial parts of the correspondence. You rewrite the proof. But some of when you refactorize, as you also do in your paper, when you refactorize, not all of them go to new ones. Some of them remain fixed, and then you can use it also for correspondence, but with a slightly modification. You need to include the trivial parts of the map that follows from the correspondence.
Okay, I think this first appears in a paper by your colleagues
Kouloukas. I mentioned that in when I said about that. I said that this is actually a generalization of this property in the paper of Papageorgiou and Kouloukas in 2009. That's exactly a generalization of this statement.
Okay. Okay, thank you.
That's exactly that. You're right. Yeah.
Me too, I have a question. Some times ago, Volkert showed us that there is a strong relation between N-simplex equations and N-gon equations.
Mhm.
So my question is, if this technique is applicable for the Lax equation for the N-gon equation.
Actually, I was very surprised.
If yes, is the relation between Lax representations for the N-gon equations and N-simplex equations?
Yes, and actually I was, first of all, as Volker said in his talk, the n-1 well-stated local, if I use this terminology, also generates solutions to the next n-gon equation. But what it was surprising, actually, I saw in is a very recent paper of Pavlos, actually, on Archive. I can send you the link. That Pavlos uses not the local one gon equation. He uses actually the same the one simplex equation that generates Yang Baxter maps. He uses exactly the same generator to derive tetragon maps. So not only it's true, but it's true some of the generators of Yang Baxter maps also work for tetragon maps, but maybe Pavlos can comment more on that.
For pentagon maps.
Pentagons, yeah, sorry, pentagon maps, pentagon, yeah, sorry.
But I expect mostly.
So instead, if I'm right, instead of in Pavlos's paper, instead of using the local 4-gon equation as suggested by Volker, I think he uses the matrix refactorization problem for simple Yang Baxter. Is that right, Pavlos?
Yes, it's correct.
Yeah.
But then, of course, you have to check that the resulting map is pentagon. It doesn't follow directly via, let's say, Volker's and yours construction. You have to prove that it's a pentagon. But indeed, yeah.
Here, let me get this straight. Are you speaking about a relation between the tetragon equation and the pentagon equation?
No. At the stage that if you take a matrix factorization problem, then you can obtain, sometimes a map that is pentagon, and some other times
sorry, not tetragon, but Bazanov-Storonov equation, I should say. So the 4-simplex equation, because the 4-simplex equation is related to the pentagon equation.
Yes, but this is a different thing. This is not via Lax. I don't know how to do it because this is the 10-term relation of Kasaev and Sergeyev. Yeah, but from Lax, I don't really know yet. Well,
but should we expect that the solution for the local problem for the, for example, for the 4-simplex equation is factorized in the form the factors serve for the local version for the pentagon equation?
Yeah.
Okay.
Yeah. Here, naively, you would think that there's a relation between Yang Baxter and pentagon equation because these equations are so similar. But this is wrong.
Okay.
Here, the pentagon equation is really a kind of subpart of the 4-simplex equation.
And it is true on the level of local of the Lax representation of this equation.
No. This is simply behind it is simply a kind of decomposition. You can think of the 4-simplex equation as being composed of a pentagon equation, a dual pentagon equation, and some additional relation.
Yes, I remember you talk very well. That's true. That's okay.
But certainly, this is not the only way these equations are related.
Okay.
For sure.
Actually, we're still studying your paper.
You have to write some simpler version.
Okay, if there are no other questions, I'd like to thank Satiris again and say
Okay, thanks very much for listening.
all
So,
of you. Thank you very much. Bye.
Thank you very much for this
yes,
nice talk.
bye. Thank
Yeah.
you. Thanks for listening.